What if I told you that the company creating the chips that power every smartphone, every laptop, every AI server on Earth has just made a choice that could make all of that technology look like a Stone Age hammer? The biggest names in computing aren't just upgrading their chips, they're tossing out the entire playbook of classical computing and putting everything on the line for a technology that runs on the laws of physics itself. And the moves they're making right now, in 2025 and 2026, aren't experiments. They're declarations of war against the boundaries of what computers can achieve. If you've ever asked yourself what comes after the Silicon Revolution, you're about to get your answer. And that answer will genuinely reshape how you see technology from here on out. To grasp why this shift matters so much, you first need to understand what classical computing really is and why it's hit a brick wall. Every computer you've ever touched, from the first calculator to the most powerful supercomputer in existence, runs on one core idea. It uses bits. A bit is either a 0 or a 1, on or off, true or false. Every calculation, every piece of software, every YouTube video you've ever streamed is, at its core, just an endless string of zeros and ones being switched back and forth at blistering speed. For decades, engineers sped up computers by shrinking transistors so they could cram more of them onto a chip and flip those bits faster. But here's the unsettling truth most people don't realize. We're approaching the absolute physical limit of how tiny a transistor can be made. We're talking transistors only a handful of atoms across. At that scale, electrons start acting bizarrely. They stop behaving like normal particles. They start acting like quantum particles, slipping through barriers they have no business crossing. The classical physics that classical computers depend on simply breaks down. And that's not the whole problem. There's another issue that even the most powerful classical computers can't crack, no matter how many transistors get packed onto a chip. Certain problems are so mathematically dense that a classical computer would need longer than the age of the universe to work through them. Drug discovery, climate modeling, financial optimization, breaking encryption, simulating molecules at the atomic scale. These aren't science fiction scenarios. They're real-world problems humanity urgently needs solved, and classical computers are, by their very nature, incapable of ever handling them at the necessary scale. That's the wall. And the biggest tech companies on the planet have just decided they're done trying to scale it. They're going to smash straight through it. If you haven't subscribed yet, smash that like button and subscribe right now, because what's coming next is information most people won't hear about for another 5 years. Enter quantum computing. It sounds like something out of science fiction, but it's grounded in real physics that's been tested and confirmed in labs across the globe for decades. Instead of bits, quantum computers run on qubits, and a qubit can do something a classical bit simply can't. It can be a 0, a 1, or both at once, in what's called a state of superposition. Take a second to really consider that. When a classical computer tackles a complex problem, it tests one possible answer at a time, working through billions of options one after another until it lands on the right one. A quantum computer can essentially explore a massive number of possibilities all at once, because its qubits can occupy multiple states simultaneously. That's not just a faster machine, that's a completely different category of machine. And there's another quantum trait that pushes this even further. It's called entanglement. When two qubits become entangled, the state of one instantly dictates the state of the other, no matter the distance between them. This lets quantum computers synchronize calculations across many qubits in ways classical computers simply have no way of matching. The outcome is computational power that doesn't just outperform classical machines, it leaves them in the dust by margins that are almost impossible to wrap your head around. Now let's get into what the biggest players in the industry have actually pulled off, because this is where it gets mind-blowing. Google, one of the most influential tech companies in human history, has been developing something called the Willow chip, and in late 2025 they dropped an announcement that rattled the scientific world. Their Willow quantum chip, running an algorithm called quantum echoes, finished a computation that would have taken the world's fastest classical supercomputer 10 septillion years to complete. Let that figure sink in. 10 septillion years. That's 10,000 trillion years. For perspective, the universe itself is only about 14 billion years old. Google's 105-qubit quantum chip cracked a problem that no classical computer could ever solve within any time frame that holds practical meaning. And here's what made the breakthrough even bigger. It wasn't just speed, it was verifiable. The result could be reproduced on another quantum machine of equal caliber and yield the identical answer. That's known as quantum verifiability, and it's crucial because it proves this isn't a one-time gimmick or a lab oddity. It's a repeatable, scalable quantum advantage. The age of quantum computing producing real, tangible results had officially arrived. Like and subscribe, because you deserve to witness history as it happens, and this is one of those moments. But Google wasn't alone in making waves. Microsoft, a company built on the software and operating systems that run the classical machines powering the entire world, decided to push even harder. In February 2025, Microsoft revealed something called the Majorana 1 chip. And this wasn't just another quantum chip. It was the first ever quantum processor built on a completely new kind of architecture called a topological core. To see why this is so groundbreaking, you need to understand one of quantum computing's biggest headaches. Qubits are unbelievably delicate. They lose their quantum state almost instantly from the smallest disturbances, like heat, vibration, or electromagnetic interference. This is called decoherence, and it's been the single biggest roadblock to building practical quantum computers for decades. Every time a qubit decoheres, it generates an error, and the more qubits you stack in to tackle bigger problems, the more errors pile up. It's like constructing a skyscraper where every floor you add makes the entire structure shakier. Microsoft chose to tackle this issue not through smarter error correction software, but directly at the hardware level. They engineered a brand new class of materials called a topoconductor and used it to produce quantum particles known as Majorana particles. These particles carry a unique trait. They appear resistant to environmental noise. They hold quantum information in a way that's topologically protected, meaning you'd have to literally alter the shape of the quantum state itself to corrupt the data. And that's exponentially harder to do by accident. Essentially, Microsoft was claiming they'd built the transistor of the quantum era. Their Majorana 1 chip currently runs on 8 topological qubits, but the architecture is built to scale up to 1 million qubits on a single chip. 1 million on a single chip. The implications behind that figure are almost too big to fully grasp. And IBM, arguably the most disciplined and consistent pioneer in quantum computing, unveiled their IBM Quantum Nighthawk processor in late 2025. This chip packs in 120 qubits connected through 218 next-generation tunable couplers. But what matters more than the raw qubit count is the quality of those qubits and the software built around them. IBM developed something called Qiskit, the most advanced quantum software platform in the world, and their newest dynamic circuit features delivered a 24% jump in accuracy at scales beyond 100 qubits. IBM has also stated publicly that their roadmap is aimed at achieving quantum advantage on a commercially relevant problem by 2026, meaning a quantum computer solving a real business challenge better than any classical method ever has. Their 2033 roadmap points toward a quantum-centric supercomputer boasting over 4,000 qubits. IBM isn't rushing any of this. They're building it with the kind of precision you'd expect from a company that knows it's constructing the most consequential technology of this century. The real-world effects of these advances are already being felt, and faster than most people would guess. HSBC, one of the largest banks on the planet, leveraged IBM's quantum hardware to boost their bond trading predictions by 34% over classical computing alone. That's not a lab demo. That's a major financial institution using quantum computing to drive real decisions and real profit right now. Ford Otosan tapped into D-Wave's quantum annealing technology to slash their factory scheduling time from 30 minutes down to under 5. Again, this is live in production, not running in a sandbox. IonQ, working with a different quantum setup based on trapped ions, ran a fluid dynamics simulation for medical device design and beat classical high-performance computing by 12%. 12% might not sound dramatic, but the key word is beat. For the first time ever, a quantum computer outperformed classical supercomputing on a genuinely commercial task that companies actually pay money to run. Like and subscribe, because these breakthroughs are reshaping the global economy, and you're watching it happen in real time. Now let's tackle something that most coverage of quantum computing gets totally wrong. People keep painting this as quantum versus classical, as if one technology has to wipe out the other. That framing is flawed, and it leads people to misread what's actually unfolding. The future isn't a world where quantum computers take over from your laptop. The future is one where classical and quantum systems work side by side in hybrid setups, with quantum processors handling the chunks of a problem that are mathematically impossible for classical systems, while classical computers manage the rest. IBM's Qiskit platform is already structured around this hybrid approach. Microsoft's Azure Quantum platform connects quantum hardware directly to classical cloud infrastructure. Google's research is heading toward quantum-enhanced AI, where quantum processors take on the heaviest matrix calculations while classical systems oversee everything else. Picture it this way. Classical computers remain incredibly powerful, dependable, and efficient for the overwhelming majority of everyday computing needs. But there's a category of problems, possibly the most critical problems facing humanity, where classical computers simply hit their limits. Quantum computers exist precisely to handle those problems. The two technologies will complement one another, unlocking capabilities that neither could reach alone. The industries set to be reshaped by this aren't small or specialized. They're the industries that shape human civilization itself. Drug discovery is probably the most immediate and far-reaching application. Bringing a new drug to market today takes more than a decade and costs billions of dollars, mostly because pharmaceutical companies can't precisely model how a molecule interacts with the human body on an atomic level. Classical computers can only approximate these interactions, and those approximations overlook key details. A sufficiently advanced quantum computer could simulate molecular behavior with total accuracy, letting researchers pinpoint promising drug candidates before a single experiment even hits the lab. The chance to speed up cures for cancer, Alzheimer's, drug-resistant bacteria, and countless other illnesses isn't a maybe. It's mathematically certain once the hardware hits the right scale. Material science is another field standing on the edge of transformation. Researchers believe quantum simulation could crack the code of room-temperature superconductors, materials that carry electricity with zero resistance under normal conditions. If that sounds dry and theoretical, think about what it would actually mean. Zero-loss electricity transmission across entire power grids, perfectly efficient electric motors, levitating trains with no moving parts at all. The energy savings alone would be worth trillions of dollars every year and would mark one of the biggest leaps in human technological history since the steam engine was invented. Cryptography and cybersecurity aren't just going to be reshaped, they're going to be obliterated by quantum computing. And this deserves its own moment of pause. Nearly every major encryption system in use today, from the security guarding your bank account to the encryption shielding classified government communications, relies on a mathematical puzzle that classical computers can't crack in any reasonable time. That puzzle is breaking enormous numbers down into their prime factors. A quantum computer powerful enough, running an algorithm called Shor's algorithm, can solve this exponentially faster than any classical machine, meaning a fault-tolerant quantum computer of sufficient scale could, in theory, crack RSA encryption, the backbone of internet security, within hours. Governments and intelligence agencies across the globe already see this coming. The United States National Institute of Standards and Technology has already rolled out post-quantum cryptography standards, new encryption approaches built to withstand quantum attacks. But shifting over to post-quantum encryption is going to take years, and the gap between when quantum computers become strong enough and when every critical system gets upgraded is going to be one of the most dangerous stretches in the history of digital security. That alone should be reason enough to hit like and subscribe, because the people who understand what's coming will be the ones ready when it lands. Financial markets sit right at the edge of a quantum shakeup, too. Portfolio optimization, risk assessment, derivative pricing, spotting arbitrage opportunities in real time, all of these come down to solving math problems with thousands of variables and heavy uncertainty. Classical computers rely on approximations and shortcuts because the truly optimal solutions are computationally impossible to reach. Quantum computers, especially quantum annealers and gate-based quantum processors, are particularly well matched to these kinds of optimization challenges. The financial institutions that crack the code on harnessing quantum advantage for trading and risk management will gain a structural edge over every rival still leaning on classical methods. HSBC's 34% boost in bond trading predictions is just a glimpse of what this will look like at full scale. But let's be fully transparent about where things genuinely stand right now, because hype is risky, and quantum computing has had more than its share of it. The current crop of quantum machines, including Google's Willow at 105 qubits, IBM's Nighthawk at 120 qubits, and Microsoft's Majorana 1 with 8 topological qubits, are impressive demonstrations and real milestones, but they're not yet the fault-tolerant general-purpose quantum computers that will actually revolutionize drug discovery or shatter encryption. The reason comes down to error rates. Today's quantum computers still produce errors at rates that demand massive overhead to fix. IBM's own findings show that current error correction approaches need hundreds of physical qubits just to build one dependable logical qubit. Google's Willow showed error rates falling below the threshold required for fault-tolerant computing to work in theory, which is a huge milestone. But getting from a 105-qubit chip to the millions of physical qubits needed for a truly fault-tolerant system remains an engineering hurdle of historic scale. Quantum computing will need processors carrying tens of thousands to millions of physical qubits. We're not there yet. But the pace of progress has sped up dramatically. The milestones hit in 2025 and 2026 are the groundwork that fault-tolerant quantum computing will eventually be built on. The honest take from the analysts and experts closest to this field is this: the era of quantum advantage has already begun in specific, narrow, verifiable areas. The era of general-purpose quantum computing is still years out, but the distance between those two realities is shrinking faster than almost anyone outside the quantum world expected. The companies pouring resources into quantum expertise, quantum education, and quantum pilot programs right now are setting themselves up to lead in a world that will look completely unrecognizable from the one we know today. What you're watching isn't a product launch. It isn't an upgrade cycle. It's a complete reimagining of what computation itself means. The race is real. The stakes are civilization level. And the companies that have stopped fighting over the boundaries of classical computing have glimpsed something most of the world hasn't yet caught on to: the next frontier of human Klaus.